spend the entire lecture for solving one problem. But the advantage is we'll review everything. In plotting the graph of a function, we'll review everything since the beginning of the semester. Limits, domain, derivatives, asymptotes. You have a solved example there for you to follow. Before moving there, we still need to finish what we found. Can I take, do you have a lecture phone? X minus normal x. So L'Hopital says if you have a limit that gives you either 0 over 0 or infinity over infinity, then you apply L'Hopital. This is it can be or here plus or minus infinity. Okay, again plus or minus infinity, not necessarily only positive infinity. Then this is the limit of their derivatives. And I showed you, I proved the L'Hopital for the case 0 by 0 over 0. Did I prove it? Did I? And then this case can be reduced to 0 over 0. Can you move here, please? The infinity over infinity can be reduced to 0 over 0. So if you have the case 0 over 0 and infinity over infinity, you look at how fast the derivatives, how fast those functions approach a or infinity. Only in this case is only when you have a fraction that gives you 0 over 0, infinity over infinity. If not, it's wrong. And I'll give you an example when it's wrong to apply it. Wrong application of L'Hopital. Let me see if I can for this one. Cos of x over x when x approaches 0 from the right. Yeah, cos of 0 is 1 over, when x goes to 0, goes to 0 with plus. You need to know the sign of 0 from the denominator when you have something like this, because 1 divided by a tiny number can be either positive infinity or negative infinity. So let's apply by mistake the L'Hopital. So if we apply L'Hopital, this says that I take the derivative of the numerator, which is negative sign of x. This one is 1, yeah. So now when I apply x going to 0, sign of 0 is 0, so you'll get 0, yeah, negative 0, 0. But this one actually gives you the limit. 1 divided by a tiny but positive is positive infinity. That is the correct limit. This is the correct limit. This one here is wrong, because you've seen the proof of L'Hopital. We use the fact that we added f of 0, f of a, g of a, which was 0. If this one is not 0, you mess up the L'Hopital. So do not apply L'Hopital blindly. You have to make sure you have 0 over 0, infinity over infinity. Yeah, so this is wrong here. This is not 0. Okay, we'll see other cases that reduces to L'Hopital. For example, you have, can you tell me what is that one, x minus ln of x? Which one is that?
6. Then we have
6?
X approaching infinity.
And it's 6?
Yes.
Lecture 12. Thank you. When x approaches infinity, you have what case here? approaches infinity. 7 is a large number, what do you get?
Infinity minus ln of infinity.
Okay, and what is ln of infinity? What is a graph of ln? And then when x approaches infinity, ln approaches infinity because this is a graph of ln. Goes through 1.
Positive infinity.
Yeah, so when you approach 0 from the right, it's negative infinity. When you approach infinity, then it will be infinity. Ln or in log. Yeah, so it will be infinity minus infinity. Why infinity minus infinity is not 0? Because what?
Different size infinity.
Yeah, and because this is a symbol, this is not a finite number. When you subtract two finite numbers equals finite numbers, of course you get 0. But this is a symbol for infinity. This may, what if this one is slightly larger than the other infinity? Then you'll get a positive number. What if this one is slightly larger? You'll get a negative. Different scenarios, different numbers. So this is an indeterminate case. This is indeterminate. Yeah. So how do you solve it? So in that list, the cases that require work, requires work is 0 over 0, infinity over infinity. Now you have infinity minus infinity. So what can we do? We can reduce this one to L'Hopital. If we force factoring out an infinity, now you will have what? 1 minus, again in the symbol sense, if we force factoring out an infinity, we'll have 1 minus infinity over infinity, which is L'Hopital here. Yeah, so let's force factoring out something. 1 that produces an infinity. Let's force factoring out an x. Yeah, so then I will have 1 minus
You got an x over x.
ln of it. Close the door. Why do I have to close the door? My door. No, it's okay. Kid, can you hear it from that part? Yeah. Okay. Ln of x over x. This is not, you do not simplify x with x. Okay, so now we check the limit. Yeah, or we apply properties of limits. Limit of x going to infinity of x times limit of 1 is 1 minus limit of x going to infinity of ln of x over x. I know what this one is infinity. 1 stays there minus, and this one here is ln of infinity. Infinity over infinity. Here is L'Hopital, yeah? So I'll take this one aside, solve it, and then go back and substitute there. Yeah, so this is infinity over infinity, therefore is in the form of L'Hopital. So I apply L'Hopital, gives me
1 over x over
ln prime is 1 over x prime is 1. L'Hopital means the derivative of numerator divided by the derivative of denominator. It's not quotient. X goes to the denominator is 1 over x, so when x goes to infinity, this is 0, 0. So now I'm going back here and substitute. So in the end, this will be what? Infinity times 1 minus 0. Yeah, so it's infinity. So still the case infinity minus infinity can be solved with L'Hopital. You have to bring it to L'Hopital form. Force factoring out 1x. 1x, 1 infinity. Sometimes, for example, you can factor out ln of x. Force factoring out ln of x. So it looks like between infinity minus infinity, we got a positive infinity. So it looks like this infinity was dominant, was greater than this one. So it looks like x is dominant compared with ln of x in the infinity. So it looks like this one. This is the x. So x goes faster to infinity compared with ln of x. Did you do number 5?
Did we?
It was a question. X cubed, no? X cubed 5. going to infinity, x cubed e to negative x squared. When x goes to infinity, what do you have?
Infinity.
Times, and what is e to negative infinity? Aside, what is e to negative infinity? Change it to a positive exponent, so it will be 1 over e to infinity, which is 1 over infinity, which is 0. When you have negative exponent, change it to positive exponent. E is more than 1, so the base more than 1 raised to a large number will be a large number. So this is 0. So infinity times 0. Why is not 0? Because any number times 0 can be 0. But any super large number times a tiny number can be that large number. Yeah, so this one can be either infinity or 0. So this is another indeterminate case. Infinity times 0. How do we write this one in L'Hopital form? L'Hopital requires a fraction. Isn't it easy to write a product in a fraction? How do you write a product as a fraction? How do you write 2 times 3 as a fraction?
6 over 1.
No. In terms of 2 and 3, I want to see only 2 and 3's.
2 over 1.
You can bring 3 to the denominator, but taking its inverse, isn't it? 2 over 1 over 3, isn't it like that? Oh yeah. Or 3 times 1 over 2, okay. Or 3 over the inverse of 2. So now here, if I write this one, infinity times 0 as what? 0 over the inverse of infinity, which by the way is what? 0. 1 over infinity is 0. So you have 0 over 0, or sometimes it's easier to send 0 to the denominator. So you'll have like what? Infinity over 1 over 0, which is infinity over 0 with plus or minus. Can be plus or minus infinity, yeah? Which is infinity over infinity. So you can change the product in L'Hopital, depending in my case, who gave me 0? This one here. So which one is easier to send it to the denominator as an inverse?
E to the negative x.
This one here, yeah. So this one, 0. This 0 will be sent to the denominator. So it will be limit of x going to infinity of x cubed over e to x squared. Yeah. So now you check the limit. This is x going to infinity. Infinity over e to infinity. E is more than 1, so it will be infinity. Now is a proper L'Hopital. Which says that derivative of this is 3x squared. Derivative of this one is not e to x, is e to a function. So that is
2x times e to
chain rule and exponential, yeah? So it will be the same exponential times inner prime, x squared prime, yeah, which is 2x. You can simplify 1x squared with 1x. And so then this limit becomes 3x over 2e to x squared. Check the limit. When x goes to infinity, you have infinity over another infinity. So you can apply L'Hopital a couple of times, but you have to see if you get a result, or what if your limit gets more complicated. Since we started with x cubed and we ended up with a linear x, looks like this one will give me a finite number, because taking the derivative of this one will be a number, will be a constant. E to x squared, all the time I will end up with e to x squared because it's an exponential. Taking the derivative, I will not get rid of the exponential. But this is a polynomial. This will be reduced in the end. Apply again L'Hopital. Now this is 3 over, and we already did that derivative of this. It's the same exponential times the inner prime, which will be 2x. So now when you take x going to infinity, this is not anymore infinity, it's 3 over what?
infinity.
Infinity, which is 0. So it looks like this one was dominant, which makes sense. The exponential goes faster to 0 compared with x cubed going to infinity. Now you can also try, or, so that is the final answer, or you can try to bring x cubed to the denominator. Limit of x going to infinity of e to negative x squared. So this one here will be x to negative 3. And check the limit. When x goes to infinity, you have e to negative infinity, which was 0, over infinity to negative 3. Infinity to negative 3, you change it to a positive exponent. Infinity cube is infinity. 1 over infinity is 0. So this will be 0. Again, everything what is here is symbolically or in the limit sense is null. So 0 over 0, L'Hopital. If we apply L'Hopital here, we have what? This one here will be the same exponential times inner prime. Inner prime will give me now what? Negative 2x. This one here is a power function. So it will be negative 3 in front, x to 1 less, which will be negative 4. So now if you simplify this one here, negative, so you will have what? 2e to negative x squared, and you can bring x to the denominator. So it will be 3x to negative 5. Check the limit, you'll get 0 over 0. Do not continue, because you notice that this exponential all the time will be there, but x to negative 3 now is increasing. Is increasing in absolute value. So you will end up with x to negative 7. So this is not a good way of writing infinity times 0. So if you started with this one, figure out if it's worth continuing L'Hopital or no, or change it to the other one. So this one will not give you the result because the function is getting more complex. So infinity times 0 is still solvable with L'Hopital. And then the last application of L'Hopital is when we have for example x2 square root of x. What's that one? Is it to 0? Is 0.
Yeah.
0 with plus. Now 0 with plus, in order to have this one defined, is a square root requires only positive numbers. That's why I put here plus. And that one is number
7.
When x goes to 0 with plus, you have 0 to the power 0. Why 0 to any power is not 0? Or why not any number to the power 0 is 1? So this one again is an indeterminate case. So what do we do with a function to another function? How can we change this one in the product? I have a function to another function. Do you remember how we...
Chain rule.
Chain rule apply. We don't have a rule for a function to another function. How would we take the derivative of a function to another function? What did we do? There is no rule for a function to another function. What did we do? How did we change this to a product? We applied...
Can we change it to quotient?
How can we change it? We need something to transform a function to another function into a product. And that will be ln. You know what ln is doing to a power? What is ln doing to a power? It's changing it to a product. And we use this one. You don't know how to differentiate this one without going through ln. So any number can be written with the help of ln, e to ln of a. So we'll be doing this one. We'll apply ln to this one. Not apply ln because we'll be changing the limit. With the help of ln, we'll be able to change this power in a product. So we'll write this one. Yeah, u with ln, they are inverse functions. So this function here will be e to ln of the same thing. Ln applied to a power will bring this one in front. So I have a product. So this will be limit of e to square root of x times ln of x. Now I apply the properties of limit, so I distribute the limit. So that limit will be e to the power limit of x going to 0 with plus of square root of x times ln of x. If I can evaluate this limit, then e to that limit will be the answer. So what is this limit? When x goes to 0, I have what? 0 times. So what is ln of x when x approaches 0 from the right? And you have the graph. I mean, you had the graph of ln. What is the limit of x going to 0 from the right of ln of x?
1. Is that 1?
X is approaching 1.
Oh, negative.
It's negative infinity.
Approaching 0 from the right.
This is 0, you're approaching 0, here is 1. This is ln or log. When you approach 0 from the right, you are here. It's negative infinity. So this will be the case, 0 times negative infinity. How do we solve it? Can solve it with L'Hopital. Yeah, so let's take this one aside, solve it, and then go back to finish the limit. So this was 0 times negative infinity. So it's the same with negative times 0 times infinity. 0 times infinity, I can write it as a fraction. Either I bring 0 to the denominator or infinity. Which one will be easy to bring to the denominator? 0, the square root of x. Because if I bring this one to the denominator, it will be ln to the power negative 1. But this one is a power, x to negative 1 over 2. Try this one to the denominator to see that actually is complicated. Yeah, so we'll put this ln of x, and here this is x to a half. On the denominator will be x to negative 1 over 2. And now when x goes to 0, check again. This will be negative infinity on top. And then here this will be what? Will be infinity to the power negative 1 over 2. You change it to a positive exponent. Square root of infinity is still a large number, so it will be 0. Why did I take this one?
Why what?
Why did I take infinity to negative 1 over 2?
Should be 0 to
Should be 0 to negative 1. 0 to any possible negative exponent. No. Yeah, 0 only to the positive exponent will be 0. If it's negative exponent, change it to a positive. So it'll be like this. 1 over, now 0 to any positive exponent is 0. 1 over 0. And since, okay, plus or minus. So it will be a plus or minus infinity. In my case, this is square root, so it's a positive one, so it will be positive infinity. So this is positive infinity. So now I have L'Hopital. Here I have L'Hopital. I don't have it at this stage. Ln of x prime is 1 over x. The derivative of this one is negative 1 over 2 x to 1 less, which is negative 1 over 2 minus 1, negative 3 over 2. So I don't have any more ln. So is limit of x going to 0 with plus, and I can bring this x on the denominator, or I can write this one as x to negative 1, and then I bring this one up. So it'll be like this, x to negative 1 plus 3 over 2. And because this is x to negative 1, then move this one up. Over, and this negative 2 will go up. Yeah, so I don't have any more fraction here, negative 2. Just limit of x going to 0 is plus of negative 2x2, and this is 1 over 2. Positive 1 over 2. When x goes to 0, this is 0, because it's 0 to a positive exponent. Yeah, so this is 0. So who was 0? The star, so I'm going back here and finish the problem. So this will be e to 0, which is 1. Yeah, so looks like this was like any number to the power 0 gives you 1. Yeah, so this was dominant. This one approaches faster to 0 compared with the linear x. And to see this is like this is square root of x, and this is x. So the slope of square root of x is steeper, is larger compared with the linear x. And there you still have examples with, for example, infinity to 0, 0 to infinity. Yeah, so you will still use ln, e to ln, because ln will help you change a power in a product. When you know how to change a product in L'Hopital, you can write a product as a fraction. So we finish with L'Hopital, which was another technique to evaluate limits. Now we are ready to plot the function, the graph of any function. Go through some steps. Questions from L'Hopital, lecture 12. We have a homework due next Tuesday. And we'll have to postpone the exam. The exam was scheduled in the syllabus on Tuesday, November 6th. So it'll be on Thursday. Complaints? Maybe you want earlier?
Thursday, November 8th.
Yeah. Do you agree? To move it to Thursday, November 8th. I will post it here in the lecture, in the next handout. So homework 3 includes L'Hopital and only this part of lecture 13, the first page. So before plotting the graph, let's see how we connect derivatives with the behavior of a graph. You know what is the meaning of a derivative? I have a function and then the derivative will be, what is the geometrical meaning?
Slope.
The slope of who?
The tangent line.
Tangent line. To f of x at the point x. So what happened with the graph? How would you describe the graph if the slope? Yeah, so here, this is a slope here. Let me color it. Since we know how to solve derivatives, we can solve first derivative, second derivative. If we have a function and we have the derivative first and second, can we plot the graph? For example, this is a tangent line. These are tangent lines. Here is equal. So if I obtain f prime of x and I obtain that derivative greater than 0, what does it mean? The slope is positive. What can you tell me about the graph of f if the slope is positive?
It's going up.
Yeah, so here is the slope positive. Here is 0. Here the slope is negative, so here is positive. So wherever is positive, the graph is increasing. So f is increasing, not the derivative. You look at the sign of the derivative and you read the graph f, the function f. F is increasing. If the derivative is less than 0, that means the slope is negative. Go down. Yeah, here is the slope negative. So here f prime is positive up to here. Here is positive. Here is negative, yeah. F prime here is negative. So the function is decreasing. What happens when f prime is 0?
It's a critical point.
It's a critical point. Doesn't mean that is a local maximum, because you can have something like this. Yeah. So here still the derivative is 0. But it's not a local maximum. This will be, you'll see later, is an inflection point. So f prime equals 0 is a critical point. But if f prime is 0, and in the left of f prime, in the left of that critical point, the derivative was positive and then negative, that means you increase, get to 0 and decrease, that will be a local maximum. So after you found the critical points, look to see what is the sign of f prime in the left and right of that point. If it changes the sign from positive to negative, it will be a local maximum. So after you solve the critical point, you will see if f prime changes at CP, at that critical point, from what? Positive to negative, that means was increasing and then decreasing, that will be a local maximum. Then that CP is local maximum. Here, I have f prime equals 0, and in the left of that point, f prime was negative, in the right is positive. So if it's changing from negative to positive, from negative to positive, what can you tell me about that critical point? So it was decreasing and then increasing would be a local minimum, L small m. So only if you look at the left and right signs of that critical point. In this case here, this is f prime equals 0. In the left of this point is positive. What is in the right? Positive. Doesn't change the sign. So that is not a local maximum. That is not a local maximum. Yeah, so here f prime is still positive. Yeah, so this is called the first derivative test. F prime will give you increasing, decreasing. And minimum and maximum if you notice a change in signs. Let's look at f double prime. What is f double prime? It's a derivative of the first derivative. Yeah, so it will be the slope of the first derivative. Yeah, so if f double prime of x is greater than 0, what does it mean?
It's concave.
The function is the function. Which function is increasing? If double prime is greater than 0, which function is increasing?
F tolerance.
F prime, yeah, F prime. Then F prime is increasing. So what does it mean F prime is increasing? The slope is increasing from a small slope. I'm getting to more steeper. For example, here F prime is 0, and then it's getting positive and closer to being vertical. Or here, from 0, so here from f prime equals 0 is getting positive. Yeah, so it's increasing. What do you notice in these cases? Okay, yeah, so in this case here, f prime is increasing. So in this part here, f prime is increasing. This is the sign for increasing. This part here, f prime is increasing. Let's find another case when f prime is not increasing. For example, this is 0, and then what happens with the slope? It's getting negative, so here is decreasing. Can you tell me a behavior of the graph decreasing? When f prime is increasing, how would you describe this behavior compared with these two?
Concave down.
Well, this is concave down, doesn't hold water. This one is concave up, holds water. This one concave up. Yeah, so when f prime is increasing means f is concave upwards or up or upwards. This will be the sign. Now when f prime is decreasing, like in this case, is concave down or doesn't hold water, so f double prime is less than 0, implies f prime is decreasing. which means F is concave down. Or this one, concave down. Now you realize that sometimes solving F double prime is much more work. Sometimes you don't need to solve F double prime because if you ended up with a local maximum, you can't have a local maximum if it's not concave down, or a local minimum. A local minimum should be concave up. What happens when F double prime is 0?
It's point of inflection.
All the time? If F double prime is 0, if F double prime of x equals 0, you cannot conclude that it's a point of inflection. To be inflection means to change the concavity. And I will give you an example when, for example, f of x is x to 4. You know the graph x to 4. It's like a parabola, it's closer to the y-axis, this is x to 4. What is f prime?
4
Of x. 4x cubed, therefore f prime of 0 is 0. So this is a critical point. Now f prime in the left is negative, f prime in the right is positive, so this will be a local minimum. What is f double prime? 12x squared, so what is f double prime of 0? Is 0? Is this a inflection point?
No.
No, because this is still concave down. F double, yeah, so for a point to be inflection point, it needs to change the concavity. So again, you have to look at the signs. What is F double prime in the left of that potential inflection point? What is F double prime in the right? If it's changing from positive to negative, is an inflection point. If it's changing from negative to positive, is this type of inflection point. Yeah, so F double prime equals 0. If and F double prime changes concavities or signs, then at that point I have an inflection point. And we are done. We are ready now to plot the graph of a function using this meaning a first derivative and second derivative. You have a solved example there? So when you try to plot the graph of all of those, one of those 2 to 5, follow the steps. First you have to find the domain. You need to know how much to extend in the x-axis. Then the asymptotes. The asymptotes requires limits. X, y intercept, and then first derivative test and second derivative test. So let's take number 4. Let's take number 4. Let's plot the graph of 4. This is lecture 13. So I need to know how much to have the x-axis. Maybe this one has only positive numbers. I don't need a lot of negative x numbers. So what is the domain? First will be the domain. Domain usually is the entire real axis except 3 exceptions. Which ones are those? The exceptions. What are the exceptions in the domain? When do you need to be careful?
When the denominator equals 0.
Yeah, so when you have a fraction, you can have denominator 0. When else? What is another exception? Square root or even root. Even root here you need to have this one greater or equal than 0. And then another one is do you see the graph of ln? There is no ln of negative numbers. So when you have ln or a log, you need to have this, the argument should be strictly greater than 0. Only these 3 exceptions. So here I would say everything except when? What exceptions do we have here? Yeah, so you have the fraction, so x cannot be 0. What else?
Ln has to be.
And you have ln, so x should be strictly greater than 0. And, yeah, so here. So you intersect this. So then it will be only 0 to infinity. So the domain is strictly greater than 0. So it will be the interval right within the interval notation. You need the interval notation to continue. Yeah, so it will be 0, infinity. So now 0 is not included, yeah, it's not a bracket. So you want to see what happens near 0. So you will take the limit of x approaching 0 from the right of that function, and here. What happens at infinity? You will take the limit of x going to infinity. Yeah, so 2 will be the limits to find the asymptotes. Yeah, so we'll take the limit of x going to 0 from the right of the function. And also you will take the limit of x going to infinity. So when x goes to 0, you have what? Ln of 0 from the right is negative infinity. So it will be negative infinity over over 0. Is this an indeterminate case? No, because this can be written as 1 over, as a product, 1 over 0. 1 over 0 is plus or minus infinity. Actually is what? Yeah, 0 from the right, doesn't matter, this is square, so it'll be positive here. Yeah, so it'll be like this. So this will be what? Negative infinity times positive infinity. Yeah? So it'll be negative infinity. This is not an indeterminate case, negative infinity. When you divide a large number by a tiny number, you'll get a large number, but you have to be careful with the sign. So do I have an asymptote here? I solve the limit of x going to 0 and I obtain negative infinity. Do I have an asymptote?
At 0.
X equals 0. Yeah, so when you have a combination of a finite with infinity, you have an asymptote and you locate the finite number, you say x equals 0. So x equals 0, yeah, x is a vertical asymptote. When I solve limit of x going to infinity, I have what? Ln of infinity is the graph of ln, so ln of infinity is infinity over infinity. So what's this? Log it out. Now, after a lot of exercises, you realize that we already solved ln of x and x. We've seen that the line x is above ln of x at infinity. X squared will be even higher. So this will be dominant, so we should get 0. Yeah, because x squared goes faster to infinity compared to ln of x. But let's apply L'Hopital. Limit of x going to infinity, the derivative of this is 1 over x, the derivative of this one is 2x, which is 1 over 2x squared, 1x goes to infinity, you have 1 over infinity, which is 0. Do I have an asymptote? Do I have a combination of an infinity with a finite number?
Yeah.
What would be that one?
1.
Who is 1? I have infinity here and I got a finite number 0. Where is 1? So how do you read the asymptote here? I said you locate the finite number 0. So who is 0, x or y? When do you read the limit on a graph? Limit is who? Is x or y?
X.
No, x is here. This is f of x. So limit of a function is the y value. So this is f of x. So f of x is y. Y equals 0. How do you read the limit of x going to infinity of this one here? When you say x approaches something, you look at the y. What is going on with y? So x approaches, like here, a will be L. L is the limit on the y. So this one is y. Y equals 0. Is a horizontal asymptote. Go back to lecture 4, I think. There I gave the definition of the asymptotes in terms of limits. You cannot solve this. You cannot find the horizontal vertical asymptotes just looking at this, because this is not a polynomial. It's a combination of ln with a polynomial. So I know what are the horizontal vertical asymptotes. Let's see where is the graph intersecting the x-axis and the y-axis. So those will be x-intercept and y-intercept. X-intercept means y equals 0. You set up y equals 0. Means this one is 0. Yeah. So when ln of x over x squared is 0. When is a fraction 0?
When top equals 0?
The numerator is 0. So this is the same with ln of x equals 0. When ln of x is equal 0, and again, you have to see the graph of ln of x. When ln of x is 0?
It's 1.
When x is 1. So I have on y, okay, let me write it like this. X is 1, therefore the point is what? 1 and 0. So the graph intersects the x-axis in 1. Y-intercept means x. You set up x equals 0. So when x is 0, actually it doesn't allow me the domain. Yeah, x equals 0 is not in the domain. So there is no y-intercept.
Because it's in the domain?
Because x equals 0 is not allowed by the domain. Yeah? 0 is approaching 0 is not 0 including. So I'm done with this limits x, y intercept. Now I want to see how is the graph approaching, intersecting the x-axis. Is it increasing? Is it decreasing? So that will be given by the first derivative. Yeah, so I'll take here first derivative. So this is 3. First derivative test. Let's go first derivative. This will give me increasing, decreasing, and possible extreme values. So I have to find f prime of x, which is taking the derivative of a fraction. So what rule is this? Quotient rule. Numerator prime gives me 1 over x times denominator. What next? Minus ln of x times 2x over x to 4. First simplify here, so you're left with an x. Then I have another x here, so I can factor out 1x, not this one. 2x is no multiple of x, 2x is multiplied with the entire ln of x. So I can factor out this x here, this x. So it will be x, 1 minus twice ln of x over x to 4. Now I can simplify 1x with 1x from here, so I left with x cubed. So finally f prime is 1 minus twice ln of x over x cubed. So I have to find the critical points when f prime is 0 or does not exist, and then the sign of f prime. So if I take first f prime of x equals 0, a fraction is 0 when the numerator is 0. And this is a logarithmic equation. Yeah? The unknown is inside ln. So I will separate ln. So if I take ln 2 ln of x equal 1, divide by 2. So I'll have ln of x equal 1 over 2. Yeah? No? 2 ln of x equal 1, divide by 2. So I'll have ln of x is 1 over 2. So what is x? What is x? Can you change it to an exponential form now?
E to the 1/2.
Is e to 1/2? Go back and review how to change a logarithmic form to exponentially is e to the power, which is square root of it. So this may be extreme value. So far is only a critical point, CP. So this may be an extreme value if in the left is changing sign with the right. So then I will see when f prime of x is less than 0. And this one is greater than 0. So a fraction here is less than 0. You cannot remove the denominator. When the fraction is greater or equal than 0, if what? For example, here is less than 0. I have plus over minus or minus over plus. You cannot remove the denominator. You remove the denominator only when the fraction is 0, because the fraction is 0 when the numerator is 0. But the sign of a fraction is given by the sign of numerator and denominator. Oh, x cubed here. So now, this is less than 0 when I have what? Negative over positive or positive over negative. But then look at my domain. I have only positive numbers. So then this one will be all the time positive. And so because x is greater than 0 because of the domain, x cubed is greater than 0. So I have a single case, which is what? Negative over positive. And so then the numerator should be less than 0 in order to give me a negative fraction. So again, you'll solve this logarithmic inequality like you solve the logarithmic equation. So you will move this one to the right, so I'll have 2 ln of x greater than 1. Yeah, I subtracted 2 ln of x. I added 2 ln of x. And then divide by 2. So I'll have ln of x more than 1/2. Now I can write this one as a ln. I know ln function is an increasing function. What does it mean, increasing function? Ln of a smaller number. If a is smaller than b, then ln will be small. Ln of a will be smaller than ln of b. That means increasing, yeah. So how do I write this one as a ln? How do I write 1/2 as a ln?
Ln and e 1/2.
Ln of e. Either you write it as a e to ln, or ln of e. It's the same thing, they cancel out. Yeah, so now, since ln is an increasing function, ln of b is more than ln of a, that means b is a. Yeah, so it's like simplifying here. It's like you remove ln, because ln is an increasing function. So you'll end up with x being greater than this one, which is square root of b. So f prime is negative in the right of square root of b. And if you do the same thing for greater than 0, if you do the same thing, you'll end up with this one changed. Yeah, this will be less, this will be less, this will be less, this will be less. Yeah, so similar to that one, you will get x less than square root of b. Yeah, so the function is positive in the left of square root of b. So it's changing the sign in square root of b. So square root of b will be what? If in the left is positive, in the right is negative, what is square root of b? How do you reach square root of b? By increasing and then decreasing. So it will be a local maximum. Yeah, so here, f is increasing on what? Increasing here, in the left. 0 square root of b. I cannot go in the left of 0, yeah, because of the domain. Increasing, and f is decreasing. It's decreasing because the derivative is less than 0 on square root of b infinity. So let's see if we need to calculate the second derivative. Maybe we can plot a graph without having the second derivative. Because we already know this is a local maximum, so you'll have to go concave down. Yeah? So let's try to plot the function. So my graph is from 0 to infinity. I don't even need a negative x-axis. And I collect all the information from here, yeah? So I have the domain. What do I have here? A vertical asymptote at x equals 0, yeah? X equals 0 is the y-axis. So it's a vertical asymptote. When x approaches 0 from the right, you are at negative infinity. When x approaches 0 from the right, you are at negative infinity. So very close to 0 from the right, you are here. Yeah, here. Then when x approaches what? Infinity, you are at y equals 0. So at x approaching infinity, you are at, so either you are here or here. Yeah? So from here you have to get here or above, so you have to intersect. I have an x-intercept at 1 and 0, so I have to cross through here 1. Yeah. So how do I go? Since this is a vertical asymptote, I have to go like this. Yeah, I cannot go concave up. I have to go concave down. So I'll go like this. Then, yeah, so it's saying that f prime is less than 0 to the right. So here, f is increasing up to 0 on square root of v. So when x is square root of v is what? Square root of 2 point something is more than 1. Yeah, so square root of v will be here in the right of 1. That one is a local maximum. Yeah, it's increasing up to that point here. Well, I don't know what is the elevation of this. Yeah, I have to find f of square root of v. What is f of square root of v? F of square root of v is the ln of square root of v over square root of v squared, which is e. Yeah. Ln of square root of v is what is ln of square root of v?
1/2 ln.
You write this as e to 1 over 2. 1 over 2, you bring it in front. Ln of v is. Ln of v is. What is ln of v? 1. So this will be 1. 1 over 2, so it will be 1 over 2e. Yeah, so this elevation here is 1 over 2e. It's 1 is above, yeah, this is less than 1. So I have to increase like this up to this point. Of course, I will increase concave down because this was an asymptote. And then what else do I need to go? I have to decrease. So I have to decrease, but I cannot go below the x-axis because I don't have another x-intercept. So I have to stay above. How can I approach this horizontal asymptote? Concave down? No?
Concave up.
Yeah, so I have to turn it somewhere because this is how you approach an asymptote. So somewhere here will be an inflection point. So we have to do the second derivative to find it. But with the second derivative, it will confirm that this is concave up to this inflection point, and then will be changed to concave the other way. Concave down, and this will be changed to concave up. So we need second derivative. And that will be 4, f double prime. F double prime is a derivative of the first derivative, which was this one. Yeah, so it will be 1 minus 2 ln of x over x cubed. Quotient rule, the derivative of the numerator is the derivative of this. Can I see on you? I want to see this. So 1 minus 2 ln of x prime. And I will finish the problem with your help. The derivative of the numerator. Only the did you get?
Oh, I haven't finished.
Oh, I thought it's finished. Isn't? How did you get one? How did you get 1/2? Can I see what you did? X squared? What was it?
Minus 1.
Why did you take the derivative of again? I don't understand.
Oh. Okay.
How do you complicate things? When you simple it, it's enough.
What is it?
What is not? What is not?
Because it should be negative. Oh, you're right.
What do you get? I want to show you the numerator.
There's no numerator?
Yeah, I'm already a step ahead, sorry.
You don't have it?
No, I mean, like, I don't have.
The numerator. It's 1 minus, not the entire fraction, only the numerator. 1 minus 2 ln of x prime. Can you, those of you who finished, can you solve the second derivative quotient rule? Now you have the numerator prime. Only the numerator prime I asked for, 1 minus 2 ln of x prime. Can I see the numerator prime? I said that this will be a review for the final exam, and I'm reviewing everything since we started. And these are derivative rules. Those of you who didn't do this part, that's a problem. This is, you distribute the derivative, 1 prime is 0. And then you keep the constant -2, and ln prime is 1/x, and it's done. Why would you take the derivative again and again and again and again? So the derivative of this one is -2/x times numerator, denominator, x cubed, minus this one as it is, 1 minus 2 ln of x times denominator 5, which is 3x squared, over this one squared. This is quotient rule. Square means to the power 6. You can simplify here, so you're left with an x squared. Now you can factor out an x squared from here. Yeah, so that will be you can also factor out the negative x squared. Yeah, so you will have 2, and you factor out this negative. Yeah, so we have plus 3, and you have the parentheses 1 minus 2 ln of x over x to 6. This will simplify, and we're left with an x to 4. So finally, the numerator is, you have a negative in front, and you have what? 2 plus 3. Yeah, so it'll be -5. And then you have minus 6 ln of x. With this negative will be plus 6 ln of x. Did you get this? We didn't get this. Those of you who solved. What did you get?
Oh, no, I have a question. Why is it 2 plus 3?
Because you had -2x squared. When you factor out the negative x squared, yeah, I factor out the negative x squared. So this numerator here, after I simplify, was -2x squared minus 3x squared times 1 minus 2 ln of x. So I factor out this x squared, negative x squared. So I left with a 2. Is it?
So it's minus 3 squared
Because I had, because what?
Because it's continuous minus the open.
Because negative was from the formula quotient rule. You have a negative, and then you have the denominator prime that came with 3x squared. Yeah, so now this is, yes.
The negative doesn't go to the whole parenthesis?
This negative here? No. So I factor out a negative x squared, negative x squared. Therefore, I left a positive in front of the parentheses.
So-
Let's not make it complicated. Let's factor out only x squared. To factor out only x squared, I would have negative 2, yeah? And then I have negative 3. Is it? So now I would have what? Negative 2 minus 3 is negative 5. And I would have negative 3 times negative 2, which is plus 6. So this is f double prime. The sign of f double prime. We have to confirm that it's concave down and concave up. X to 4. X to 4 is all the time positive. So the sign of this fraction will depend only on the sign of the numerator, yeah? So f double prime. Okay, so here I will say implies, because x to 4 is all the time positive, then there are still spaces here, but there is no time now to move if you don't see anything in this side. Yeah, so as long as I can write this one as a ln, then ln of x will be more than ln. I can neglect ln because ln is an increasing function. How do I write 5 over 6 as a ln? Ln of what? E to the power 5 over 6. 6. So x will be more than, so from here, x will be more than e to 5 over 6. You know, when you have an exponent with fraction, that will be a radical, yeah? 6th root of e to 5. So f is what? If f double prime is greater than 0, that means f is, no, this is f double prime, it's not f prime. Concave up or down, yeah? Concave up in the right of e to 5 over 6. Okay, concave up, yeah? So here, f is concave up. You understand what is this? Concave up. On what? E to 5 over 6 and infinity. And you will figure out if this is less than 0, this sign will be less, this will be less, this will be less, yeah? So f is concave down like this. On what? When? In the left of. Left cannot be more than 0, so e to 5 over 6. So now, it looks like this one is e to 5 over 6, but you have to confirm that e to 5 over 6 is in the right of square root of e. How do you show that e to square root of e to 1 over 2 is actually in the left of 5 over 6? Because if we get something that is here, is not confirming our figure. E is more than 1, so only if the exponents are 1 over 2 compared with 5 over 6 is, yeah, so 6 is less, so this is less. Because these are less, yeah, because 1 over 2 is less than 5 over 6. So here will be e to 5 over 6. Yeah, concave down in the left of 0 and 5 over 6, concave up. So it's changing the concavity. So this is an inflection point. So we solve this one. This is an inflection point. So that means to graph a function, to go to find all those critical points, all those intercepts, a vertical axis, vertical asymptote, horizontal asymptotes. And now you can confirm with the graphing calculator. You'll plot this one, or you'll use Wolfram alpha. In Wolfram alpha, just Google Wolfram alpha. And you'll say plot, and you'll say only what? The right hand side, ln of x divided by x squared. For the homework, when you go through all of these steps, you can confirm with the plot. You can imagine in the exam, if you mess up with f prime, your f double prime will be wrong. So that's why I will say show that f prime is this. So if you didn't get to this one, you try hard, you didn't get the result. When you have to find f double prime, you will take the correct f prime. So in this way, you will not be penalized twice for that mistake and then here. Yeah, when I will say show that f prime is that, you have to do all the calculations to find f prime. If you don't find it, that's okay, but then calculating f double prime, you will take the correct f prime. So for 1% is enough if you take only one problem from here and do all the steps to get the graph.
For 1%?
For 1%, because this is intense work.
So if we do 3, we get 2%.
Yeah. But not only the graph, all the work that supports the graph. Okay.